It's my pleasure to introduce our keynote speaker for today, Torsten Hoefler from ETH. Yeah. Torsten.
Thank you very much. Thank you very much. So wonderful to be here. I want to start with a live demo. And let me see, live demos usually go completely wrong. I do have a backup, but this one, let's see. So here's Microsoft's Copilot on the right side, which is a chatbot, something I'm going to talk about today, and I'm going to explain how it actually works in detail. But let's ask it the question about our meeting here. What is the most interesting, let's say, scientific event today in Locarno, Switzerland? Okay, so let's see what the chatbot says. It may go completely wrong and everybody is leaving in a minute because there's something more interesting. But it's a little bit slow, and we'll also be talking about this. Oh no. Damn it, see, I told you it would go wrong. Okay, let's not try that. The funny thing is, so let's close this quickly. The funny thing is I've tried that before, that exact thing, and I have it actually recorded on the slide, and it was telling me the HPC Advisory Council. So see, every time I do these demos, it goes wrong. But you can also see that these chatbots are not very deterministic, and we'll see why they're not very deterministic. But actually, the right answer would have been HPC Advisory Council, organized by, co-organized by CSCS and Brian and people, and then great. So, well, we'll see. Okay, wonderful. But let me now explain a little, so I can go back. Let me now explain a little bit how these chatbots actually work in practice. And this will be something surprising because you just saw this non-determinism, which surprised myself, but I tested it twice before. It did work twice before. So why did it not work now? You will understand in a couple of minutes. But I want to first explain a little bit more how these chatbots actually work, because we have many of these chatbots. We have Copilot that I just used, ChatGPT, Claude, and many, many other things that you've probably been interacting with and you use on a daily basis. But at the end, how do they work? Because they're an HPC problem. And this is why I want to mention those here. At the beginning, we start from raw data. We start from data on the internet. We have lots of data on the internet. In fact, I would argue that pretty much all of human knowledge is represented on the internet. Everything we know, everything we do, at least to some extent, is somehow captured in text form on the web. What we do then is we pre-train a very large language model. And these LLMs are really very large. So they have somewhere between 2 billion to a trillion parameters, and that's a very large number if you think about it. That's multiple gigabytes in size just to store the size of the model. But then this model, this pre-trained language model, is not a very good way to interact with humans. So what we do then is we take this and we apply something that's called supervised fine-tuning to actually make it a little bit more amenable to humans, so to turn it into a chatbot. So for example, the original pre-trained LLM, all it can do is it can complete text. It's literally an auto-completion framework, which is not a very entertaining interaction device. So now we tune it to be nice to humans. In fact, we do this by using humans as a supervisory object. So humans tell or rank the kind of silly chatbot at the beginning how to behave, which is very much like we train our children. We actually train our children how to behave, and this is exactly how this works. If you look at the prompts, if you look at the value function, of course the value function here is a number. Our children usually get food or padding or some kind of love, but at the end it's very, very similar. So, but then the problem is to train a chatbot, we need a lot of data, a lot of data. So humans don't have as much patience. As you may have realized, humans learn much faster than computers, which is true. So a computer needs about 1,000 times more effort to teach it the same thing, like a language model, than a human. A human I'll tell once, maybe twice if the human is not so smart. A language model I have to tell about 1,000 times before it actually takes something. So it's very annoying. What we do then, to make this a little bit better, that we don't employ all these humans, we actually train another model that learns to train the model to be friendly to humans. This is called a reward model up here. So there's actually another model that judges the output of the language model such that it says, well, whether it is a good answer to humans, whether it's a pleasant chatbot. And then you do this over and over again. And then at the end, if you use this model-based supervision thing, you train this for months on a very, very fast computer. And this is what I will be getting to in the second part of my talk. And you will get to the fine-tuned language model, which is essentially our chatbot. So you can actually skip all this thing. You can today go and download this. Meta has done all of this. You can download the Llama 70B model. You can download the Mistral model. And you can run those not quite on your laptop. unfortunately. You can run the small ones on your laptop. The big ones you cannot run on your laptop per default. However, during this talk, I will tell you how you take these large models that are multiple hundreds of gigabytes in size and compress them to a size and accelerate them to something that you can in fact run on your laptop. So I'll start from the supercomputer, how to train these very large models, then I go to the artifact, and then we go how to move them on your smartphone. This is why AI from supercomputers to smartphone. But let me go a little bit more into details. This is now the human interaction here, this is how the chatbot works, we've just seen it, and then we get replies from the model, okay? So this pipeline is changing every couple of weeks. It's actually it's a very active field of research. However, that's the latest snapshot that I'm aware of. So what do we now do with this pipeline? We actually have two things that we need to worry about here. The upper part, which is training, where we train these models on the largest supercomputer infrastructures on the planet. So if you look at the amount of money invested in supercomputing, it is now dwarfed by the amount of money invested in AI training, by at least a factor of 10. So you've seen the stock value of NVIDIA, which is mainly driven by this. Right? They had a little bit intermediate, good time with cryptocurrencies, but now it's all AI. So that's basically, that's something I will talk about the first 20 minutes of my talk. And then the second part, I want to go a little bit more into inference-related things, because that is the new upcoming business. Because now we have these chatbots, but now we have to learn how to use these chatbots. And at the very beginning, you've seen that I completely failed to do my demo, so we don't quite understand how to use these chatbots. It's actually a good introduction, this failure. So we can make them use tools. We can make them actually behave like humans. We can do psychology of language models. There are many people now doing psychology of language models. Why is that an interesting topic? Because these language models are literally trained on all the data that humans have ever generated. They're trained on books, they're trained on feelings, they're trained on phone calls that we have. They're trained on talks like I'm giving right now. This talk will go on YouTube. I'm 100% sure that at least a dozen language models will be listening to what I'm saying right now. They will ingest that knowledge into their knowledge base. So somehow you could argue that these language models, they learn from human thought, because our language is nothing but an expression of our thought. And this is the only way we can express our thoughts. This is our way to link two brains. Actually, in my case, I'm linking now my brain to many brains, to your brain. So now imagine that is now the basis for training these language models. These language models learn to behave like humans, learn to actually be like humans, if you want to be a little bit more philosophical here. And again, I'm not saying they are humans, right? Keep that in mind. But it's a very interesting discussion. Then these things know how to behave, know how to read the web. What I showed at the beginning, Copilot, was actually looking up information on the web. It was probably getting a slightly wrong query and thus not giving me the right answer, but that's what it can do. It can do information retrieval, very important for personalized medicine. And at the end, it's all about using the right prompt, using the right prompting structures. And here, this is a little bit of an art. And I want to give you a little bit of an introduction how to prompt correctly. And now you think, why am I learning from that guy? He messed up his demo at the beginning. Yeah, well, you know, that's not up for you. You should probably go and read email for the next 10 minutes, and then we'll see. So how can we prompt language models today? And I can tell you the mistake I made, because I used only the basic input-output prompting. I had a single prompt, and I asked for a reply. Right? So this is what most people do today. It's called basic I/O prompting in the literature. So this is how it goes. So you have some kind of prompt here. You may be giving it an example if you're nice, and then you ask it a question, and then you get an answer. And in this case, if you actually are fast enough to follow this thing, you will get the wrong answer. So you give it an in-context example, but you get the wrong answer. Okay? But now, you could do something quite nice that's called chain of thought. It's a pretty big thing that just came up 2 years ago. So who has heard of chain of thought? A couple of people, so about 2%, I would say. So what is chain of thought? Chain of thought is the idea that you now give the language model, instead of just saying, here's the question and here's the answer, you give it reasoning. This is literally how you would train your child. You would not, if you would explain your child how to solve this thing, you would not tell the child the answer is 11. No. You would tell the child, well, you know, Roger started with 5 balls, then 2 cans of 3 tennis balls, blah, blah. This is how you get to the answer. This is how you would train a human. Very similarly, a language model reacts to this. Okay? So now the interesting thing is, the language model, it's actually has seen many of these examples. It's already in the training database. It's already in the training data set, I mean. So what you can now do when you ask this question, you just need to remind the language model that it has many of these in-context examples. So very often, if you just go, let's proceed step by step, the model will get this hint and go step by step. Many many providers of language models today, in fact, have this in their backend, so you don't need to say this anymore. Like they just add it for you. But it's quite an interesting discussion. So what happened then? Well, what happened? You could use, this is one chain of thought, as I just described. If you just ask the model, go step by step, right? That's essentially the simplest form of chain of thought. Then there is multiple chain of thoughts where you can evaluate multiple in parallel if you have a lot of money, and you can discard n-1 of them and then just pick the best one, right? But it's extremely expensive. Then you have tree of thoughts where you could actually early abort some of your reasoning chains, right? So you realize you're running into a decision where which is not very useful, and then you have that. But let's try that in practice. So I mentioned that I wanted to give you a little bit of an insight how we do this. So we can, there's lots of prompting guidelines and how-tos. So let's do a prompt. So what's the capital of Australia? That's a real prompt from a couple of months ago. So can anybody help me? Oh, that's the wrong answer. So Canberra. Most people would intuitively say Sydney. This is a common misconception. And this is actually in the training data set of ChatGPT or of whatever the model is you're using. So if you just ask like this, the immediate thought many people have is Sydney because it's the most well-known city in Australia. Right? That's where the opera house is and that's where the fireworks are. But now, if you ask the language model, this is a real example, are you sure? Well, it'll actually be, oh, you know what? It's really like you think. Right? When you ask me capital of Australia, my first thought, oh, Australia, Sydney. But then it's like, oh, wait, actually, no, it's probably not. So it's very much the same. Mark Josinovich, one of the CTO of Azure at Microsoft, he has actually seen something very similar just a couple of weeks ago on February 14th. So no, it's 2 months. And he posted about it, so I found that also entertaining. Also, ChatGPT has these issues. So this is what chain of thought is. And now the next step of this is really to make these models reason a little bit more, but make them reason like human thoughts. So how do we go as a human? So when I want to solve a very complex problem, what am I doing? So I'm a scientist. I have complex problems, so what I do is I hope to come up with a good idea. Then I realize maybe that's not a good idea. I come up with the next good idea, a slightly better idea, and then I may be fusing those two ideas and come up with a really good idea. Then I may be writing this down because my brain is not very good. I'm, of course, forgetting these things. So I write it down. Then I'm going on a run because when I'm going on a run, I usually have more good ideas. Right? So this is how we work. Then I write those down, I merge those, and then I go on a run again because I think, oh, it's a good idea. And then I may be finding my solution. Right? So that's how humans typically work. But now, how is this actually relating to the biological brain structure? I could give a talk about that, but that's not the topic of the HPC Advisory Council. You can actually look at this paper. It's quite interesting. Torsten identifies 3 different basic features of the human brain: recursion, hierarchy, and sparsity. We will be talking about hierarchy and sparsity in this talk from a computational perspective in a couple of minutes, not from a brain science perspective. He's a brain scientist, Torsten. But just as an intuition that there is some relation between this. So what did we come up with in my group? Just last year, we invented this graph of thoughts, which is a more complex version, where we can actually have multiple intermediate steps. And the idea here is that we can treat these intermediate outputs like thoughts. So we can generate thoughts, we can enhance thoughts, and we can aggregate thoughts. That's the fundamental principle. I don't want to spend too much time on this because it's not very HPC related, but it is very HPC related, as you will see, because we need gigantic computing power to make this happen. You've seen the Copilot output. It took quite a while. It actually takes multiple milliseconds per token. This compute workload for running inference today is going to be the most cycles that humans spend on anything, like compute cycles, very, very soon. So inference is going to be the most important workload of humanity, very, very, very soon, in terms of cycles consumed. So now if I ask you to sort, how would you sort? Well, many of us have a computer science background or a mathematical background. I give you this sequence. You would not be crazy enough to try to sort this sequence directly. What you would do is you would probably cut the sequence into smaller sequences. You would call this generate, maybe. Then you would sort each of these sequences, and then you would merge these sequences back into a sorted sequence. That's how a simple sorting algorithm works. In fact, you can do this. You can do this with a language model. You can do this. You can ask the language model to do exactly this. It's a little bit more complicated. I don't want to go into much detail. But if you really care about this, you could go and look at this on our paper that we just published a couple of weeks ago. Now it actually appeared last week at AAAI. So that is how you can use these language models to do bigger things, right? on top of the language model. But you basically need a supercomputer underneath to do all of this, because this is going to generate thousands of prompts automatically. So this is the next level. The first level is to talk to the language model like we have been doing this, or I have been doing this with my botched introduction, right? But the next level is to have these language models talk to each other, to argue, to form little computer societies, and talk and solve problems. And this is a very interesting idea. But now, how did we get to this amazing technology that we can now use to do all kinds of cool stuff? Well, first we had a lot of data. Actually, going back a couple of years, the world's most valuable resource is no longer oil but data, right? So that was in 2017. And we can go, well, the data is the new oil of the digital economy. Data is the new oil, and now, we have to avoid data fires, so it gets a little bit more fishy. That is about 2022. So just 5 years later, data can be a problem. And actually, if you now think about this, Sam Altman just tweeted also 2 months ago, OpenAI now generates 100 billion words per day. That's a lot. All of humanity just speaks 100 trillion words a day. So basically today, where not everybody is using language models every day yet, right? We are already at 1,000th of the total spoken words on the planet, which means we will actually be exceeding these language models once they start talking to each other, like I mentioned, graph of thoughts and all kinds of internal talking, they will be exceeding humans in generating words, which is quite an interesting thought, like if you have enough compute power. So there's a second problem with this. If the humans are now generating data slower than the language model can consume it, right? Because language models generate now more data. This means we will be running out of human data to train on very, very soon. Right? So many people are already pointing this out. On the language side, we are essentially already run out of data. We have a lot of image data that we can now feed. Multimodality now comes up and all of these things. But still, we may be running out of data. And now the next step is synthetic data. So what is synthetic data? Synthetic data is the data that we just talked about in graph of thoughts. A language model generates data, or a model generates data, and the model learns from itself. Right? So that's synthetic data. What this really means is that we are in the right job. Because this is all computation. Right? It's not data is the new oil, but we will be running out of data. The next new oil is computation, because computation can generate data. That's just as a motivation. And people have recognized this. So this young gentleman, just a couple of months ago, announced that by the end of the year, Meta, a company that made Facebook, and actually is a social networking company, they're going to have an equivalent of 600,000 H100 compute power, H100 device compute power, just in their company by the end of this year. So we are already in April. I don't think they will actually be able to purchase all of this, because NVIDIA doesn't actually deliver any, or not much, because they're at their limit to deliver things. It's not their fault, but it's really the demand is so high. But that's what it goes. So this is going to be an $18 billion investment. And I always say when I give these talks, in the good old days, rich companies that had a surplus of money were acquiring smaller startup companies to build their future. Like Microsoft acquired LinkedIn and Skype and all of these smaller companies. Today, rich companies acquire compute power to build their future. Think about that. It's a complete game changer. Right? So now everybody believes compute power is the thing, so HPC is the thing. Now an audience question, we all know this top 500 list. Right? Top 500 list, in case you don't know, lists the 500 fastest computers, publicly known, I have to say now, because I know of faster ones. 500 fastest computers on the planet. The compute power that just Meta alone will have, how many top 500 lists is this? Complete lists. 0.1? 0.5? 1? 10? Anybody? Well, I can give you a hint. The total top 500 performance today, on November, or last November, was 8 exaflop, FP64. Now, if you know what the performance of a single H100 is, you multiply this by 600,000, right? And then you know it, if you're fast. So who gives me an estimate here? Can anybody give me an estimate? Come on, NVIDIA people, you should know your architectures. Aw. Okay, so it's going to be about between 5 and 7 total top 500 lists. So a single company acquires this much of compute, right? So that's crazy. It's completely crazy if you think about it. I'm actually going to follow up with Mark and see if that actually happened. But at the end, what's happening now? Everybody builds supercomputers. Facebook, Tesla, a car company, Google builds supercomputers, Microsoft builds supercomputers. Just yesterday, they announced that they're going to invest $1.8 billion in the Middle East in supercomputing. And this is crazy. It's like our field is taking off. And what's this all about? This is all about language models. It's essentially all about one workload that I'm going to explain in the remainder of the talk. I know my introduction is quite long, but I wanted to convince you that this is really an important workload. And this workload is what I'm showing here, and I can explain it in about 2 minutes. So you'll be an expert in how language models work in about 2 minutes, because it's really simple. We take text off the internet, like from Reddit, that was the original one. We remove a word from that text. Just pick a random word, like here. You can all see what I removed, right? Then we run it through a function f of x. This function is parameterizable. It has a transformer structure. It's a generative model. By the way, GPT stands for Generative Pre-trained Transformers, right? So it's a transformer model. And then what you do, or what this model does, it gives you a probability distribution over all possible words in the language. I'm just showing 7 here. In fact, in reality, that would be 50,000. It doesn't fit on the slide, so I'm just showing the top 7. It gives you the probability distribution, and then you see the most likely word would be not, right? But the second is sometimes, it's also kind of likely. But sometimes a not are close. But then, of course, what you know is which word you removed from the text, right? Because you removed it, you can just remember it. And then what you do is you update this model, this very, very large function, you update it such that in the next iteration, when it runs forward, it's more likely to predict the correct word. And this you do trillions of times. Like, it's not billions anymore. We do this trillions of times today. We run this trillions of times, this loop. So for GPT-3, that's the last model I can really talk about, unfortunately. It's quite old at this point. We had 500 billion tokens, so 500 billion words in the corpus. It's actually the whole internet today. It has 175 billion parameters. Today, we know of models that have more than 1 trillion parameters, like Gemini kind of admitted to this. So. And others exist. So that 175 billion is just 700 gigabytes of data, so it doesn't fit in your cell phone, right? So that's pretty, at least my cell phone. You may have better cell phones than I do. And then it takes weeks to train on the largest machines on the planet, okay? So let's now accept that this large-scale AI is the future. So this is really, I would say, the future of all of our, of what we do. And now we need a principled approach to this. And in the next couple of minutes, so I still have about 35 minutes left, I will tell you how to improve this workload by about a factor of 1,000. This is going to be relatively fast because there's a lot you have to do to get a factor of 1,000. But I'm giving you an overview of these techniques such that you remember, it's a keynote after all, such that you remember the high-level parts of it. So how do we get there? So there are 3 different dimensions, and these are actually all HPC things. So there's nothing very specific to AI. And there are actually things that are specific to AI, but I'll be pointing them out very specifically, very separately. So first you need good I/O. Then you need good compute. Like at the end, HPC is called high-performance computing, so you need fast computing. And then you need, in order to enable fast computing on very large machines, actually all about communication. So this meeting is very much centered around communication, around networking, because communication is the key of high-performance computing. And everything else is not super mega interesting. GPUs made it slightly more interesting because they're harder to program than CPUs. Well, used to be harder to program, but at the end, it's all about communication. I have to skip this part because first of all, in language models, it's not interesting. I/O is not very. I'm sorry, DDN. I/O is not very interesting for language models because text is a very small. Text is a couple of kilobytes. The whole internet is less than a petabyte. So who cares? The whole internet tokenized with all the relevant text is very small. So I have this in the full talk on YouTube. If you do image processing, if you do AI for science, then you have a problem because just the ERA5 dataset for climate prediction is 5 petabyte. And we are talking about hundreds of petabytes and actually exabytes in climate sciences that we need to feed through similar models. So I'm not saying it's irrelevant, just saying for the language models, it's not super relevant, okay? Then the compute I'll be talking about and the other parts I'll be talking about. So the first thing I want to hammer into your heads, in case you haven't gotten that yet, it's all about data movement, right? So compute actually performing the actual arithmetic operation is nearly free. It's negligible cost. It's all about moving the data at the right location, and that is at all levels. That's at the network level, at the cluster level. It's also at the chip level. So inside my chip, I need to move the data from the right registers to the right side. Here we have NVIDIA GPUs, for example. They're very generous in some sense. They have a global register file. They have a global scratchpad memory, global to an SM, so it's already partitioned in some sense. The next generation will be more partitioned, I'm pretty sure. So I don't know details, but everybody is going into more partitioning. You need to worry more about locality. So what do? You now take this model. This is again the same model, the same transformer model that I talked about earlier. It's the basis of ChatGPT. So it's exactly the same computation. And then you realize it's really expensive to train this thing. The original version was about $12 million to just train it. By the way, fun fact, if you read the original paper, they had a bug in it. But there is actually a bug in this code, in their data preparation. They admitted it in the paper, but they also say it's too expensive to retrain, so we just have to live with the bug. So that's how it goes today. But now if you look at the actual computations in these models, this gets very interesting, because there are basically three different types of operators or of calculations. One is tensor contraction. That's basically matrix multiplication. Jack Dongarra fixed that for us, right? So he got the Turing Award for LinPack, which is essentially matrix multiplication. This is 99.8% of the floating point operations of a realistic model, okay? So that's basically everything. But then we have two other operations, statistical normalization and element-wise operations. These are nearly trivial. I mean, this is softmax essentially and layer norm. And the element-wise is just GLU or ReLU or whatever you use. So nearly trivial operations. But what is very interesting is that due to some twisted form of Amdahl's law, these tensor contractions, they got so fast. People have been tuning these matrix multiplications over decades. In the latest, or in a couple of two generations ago, in the Volta architecture, NVIDIA introduced a special matrix multiplication unit that they call tensor cores, because tensor sounds much cooler than matrix. Of course, you have to call it a tensor core. And Google before also called this the tensor processing unit, because of course tensor sounds much better than matrix. At the end, it's not really tensors, by the way, and we can talk about that offline. So this is extremely optimized on every architecture. Even Intel CPUs have now the AMX extensions, advanced matrix extensions. ARM CPUs have a similar thing, scalable matrix extensions. So everybody has specialized units for this kind of stuff. What does this mean? Now these 99.8% of the flops are really, really fast, right? Which unfortunately now makes this other stuff relatively really, really slow. So these 0.2% of the computation, they cause 40% of my runtime, which gets really annoying. so think about this. 0.2% of my floating point operations cause 40% of my runtime. So this is annoying. So we realized this a couple of years ago. And then we found that, well, maybe we should not be optimizing matrix multiply anymore because we have optimized it so much. Maybe we should look at the other stuff that's going on. And this is what we did. And we basically got an improvement that would have saved about $3.6 million to train the GPT-3 model if they had it before, but they didn't have it before. This is by now adopted in pretty much all production models. I just want to give you a high-level overview. And what we did is we looked at this multi-head attention. This is more complicated than I can explain in the 2 minutes I have for this. But what we basically did is we looked at the detailed data flow of this overall model. We used our data-centric programming environment for this. And then we looked at the different layouts you can actually lay out these tensors. Because a tensor is nothing but a high-dimensional matrix. Let's say it's a 4-dimensional matrix, dimensions A, B, C, D. This is all linear in memory. Now you can store it as BCDA or as DABC. Right? All of these different permutations of the dimensions change the linearity in memory. This is very, very relevant for cache behavior. It's very, very relevant for prefetching, for the NVIDIA subsystem, which is not sometimes troubled with some memory accesses. You can see there is a factor of 10 difference between the worst layout and the best layout in each of these cases. Right? So we have to find a good data layout. This is not easy. A second thing what you typically do in these models is you can fuse together various operators. You see each of these boxes here as an operator. Now, these are all looped operators. They all operate on matrices. And each of those is a separate loop, usually. But I can fuse these loops together. But actually, fusing together has upsides and downsides. If you fuse too much together, your compiler is not doing a good job in register allocation. If you fuse too little together, you have too much looping overhead of just maintaining the loop variables. So this is also about a factor of, here is a factor of nearly 100 from the worst possible fusing to the best possible fusing. So it's very relevant. And then, of course, we have to combine these two strategies into an overall selection method. More complicated, you can look at the paper, it's an archive, it's up here. And then at the end, what you will get is you will get a performance improvement that's quite significant. In fact, there is this deep speed team at Microsoft, and as I mentioned, Microsoft was investing $1 billion into this. They built very large infrastructure at the time, so they had a team that did nothing else but optimize these codes, right? We beat that team still by 50 and 20%, because we looked through an extremely large configuration space which no human could do. We basically automated that whole thing. We burned a whole lot of GPU time to look through the configuration space, but at the end it was worth it. So now we realize that moving data is most expensive. Like the most efficient optimization of these workloads is not improved matrix multiplication. That's just the baseline. It is to move the data in the best possible way. Now the obvious question is now, well, why don't we reduce the data? Why do we have this frickin' 700 gigabyte of data for the model? Why don't we make this smaller? Exactly. There's a technique in machine learning that is called quantization. And the idea there is that we take these 175 billion parameters that are by default stored in each parameter takes a 32-bit value, right? So that's a lot of bits. That's 4 bytes. That's large. Now, my brain runs at a very limited precision, as you can tell here. So it's not 32 bits. So actually, if I look at this, if I look at the scientific studies of how many different levels a typical human brain can differentiate, different voltage levels, it's 24. So there was actually a study that measured what a neuron can differentiate. So the resolution of a neuron is 4.6 bits in a typical human brain. Like, of course, it varies. I mean, mine is less, yours is higher. But let's say you have 5 bits, right? So, and I have 4 bits. And then the problem is now with these 175 billion parameters, if we go from FP32 down to 4 bits, that's already a save of about 8x, right? Is it 8? No, it's, yeah. So that would be nice. Actually, what's quite interesting, if you just round these values, if you just take these 175 billion parameters and round each of them down to 5 bits, right? This integer bits. This will actually work reasonably well, and the language model will not be much worse than it was before. Right? So that's number one. However, if we go lower, if we want to go to actually 4 bits, you can see there is some kind of weird relation between these 4.6 here. Right? If you want to go lower, then you need to play a lot of tricks. And I want to tell you about one trick because it's quite a cool trick. It's very easy to remember as well. So the way we train a language model is we use stochastic gradient descent to optimize it. We have a large-scale optimization space like this. I'm showing a one-dimensional optimization space here. This is my loss function. This is actually the cost of the my loss function that I mentioned on the first slide or on the second slide in terms of how bad the model is. So the lower, the better. And this is my one parameter. I'm showing a one-parameter model here. Imagine this in a 175 billion dimensional space, right? I cannot even display a 2-dimensional space here. I'm displaying a 1-dimensional space. But the real one is 175 billion or a trillion dimensional space. So keep that in mind. But now we start at a random location. So you initialize your parameters to some random value, and then we do stochastic gradient descent. So you go down to some local minima. That's how it works. That's it. Like you train, you do SGD, and you go down to some local minima in all of these billions of dimensions. Okay, and now you can actually express this as you can expand the loss function into its mathematical form with these 3 terms. And so what are these terms? So the first term is the gradient of the loss function. If you're at a local minimum here, after you've trained your model, you're at the local minimum, the gradient is approximately 0. Like if the gradient is not 0, you have not trained correctly. We are talking about quantizing a trained model here. We hypothesize that the higher order terms of this function are actually not too relevant. So we say, that's also approximately 0. So we assume that this is not 0. It depends, this depends a lot on different loss functions, and I have a lot of discussions about this. However, it's approximately 0. So what we focus on is only the second order term. And if you're now a mathematician, you immediately recognize, well, the second order term in a loss function or of a derivative is the curvature of the derivative. It is how steep you are around the place you're sitting, right? So now I'm showing 2 parameters here, x2 and x1, and I'm showing you the loss function, the curvature of the loss function. So here is the minimum, and this is just the gradient display. So now, if I was asking you, now you should decide which one to round, x1 or x0. When you round it, let's say x1, the next representable number is here. For x0, the next representable number may be here, right? Which one would you round in order to minimize the rounding error? Can anybody help me? x1 or x0? x1, exactly, x1, because it's much flatter in this dimension, right? And this is exactly what we do with the technique that is currently the best performing technique for for quantizing these language models. We just do it not in a two-dimensional space where you could easily see it. We do it in a 175 billion dimensional space. We have to compute the inverse Hessian matrix for a matrix of 175 billion times 175 billion in size. That's not possible, okay? You cannot do this. You cannot invert a 175 billion times 175 billion matrix with today's compute. But actually, you can approximate this, and you can find this in this paper, which is still one of the best methods known to quantize these language models. So you can phrase it nice mathematically. You have to do this inverse Hessian that I just mentioned. It's complicated. I don't have enough time to actually explain the details. But what we do is we do an approximation to this inverse Hessian, and we solve that. And at the end, what the final result is, we actually get easily down to 3 bits. We trivially get down to 4 bits without significant loss. We can get down to 3 bits. In fact, we can get down to even 2.5 bits in the latest version, right? So 2.5 something. Ask me offline about this. So we basically now just reduced the data cost from 32 bits to about 3 bits. That's a factor of 10, right? That's good. I promised you 1,000, so I have to give you 2 other factors of 10 in the next couple of minutes. So how do we go further? The next factor of 10 we get out of sparsification. It's also something very natural if you think about how the brain works. So brains are not densely connected, right? So in some sense, a brain is this wobbly structure in our head that is kind of living in a 3-dimensional space full of water, a little bit weird if you look at it in reality, and has a lot of connections. But these connections are local, they're local and global, they're long and short ones, but it's definitely not that every neuron is connected to every other neuron. That's not the case in the brain. In fact, it's about 20% density, like 20% connectivity. So, and this is really, the problem is in our DNN computations today, we use dense matrix multiply, which essentially connects each layer, each neuron in layer I with each neuron in layer I plus 1. Right? This is what we do. This is what dense matrix multiply does. So that's kind of weird. Why do we do this? Well, we do this mostly for technical reasons because SGD doesn't really, we don't really know how to make SGD work on sparse. This is a huge research question. I'm working on this since a long time and I still don't have a solution. So it is problematic. However, once we have trained the model in dense, we can go and sparsify it. We don't know how to make SGD work to train sparsely, which would be great, but we can sparsify it once the model is trained. Because not all these features are always relevant for inference. What does that mean? Well, look at this sentence. I think you all can read this sentence. Even though it's missing 1/3 of the letters. So this is an intuitive way to explain to you that not everything is needed to actually do, to process information. And in fact, you can do this in a language model. So you can take many of these neurons here and just remove them, and it'll still do fine. It'll still do exactly as good as it was doing before. You just have to figure out which of those neurons you want to remove. Right? You cannot remove random ones. That's not going to work well. You can also remove connections like these guys down here. So in practice, what we have managed to do is we have managed to reduce or remove 95% of the parameters. So keep only every 20th parameter in ResNet models. And we've managed to remove about 60% of the parameters in large language models. So unfortunately, large language models are still an open question how to do this. But we have gotten BERT down. BERT is kind of like a mini LLM in some sense. It was the first one. So we're still hoping to get to the final result. There's too much to talk about in this allotted time. So again, there is of course much more literature out there. There's actually, if you like listening to me, there's a whole YouTube channel of hours of tutorial. There's actually a 4-hour tutorial just on sparsity alone that I'm giving, because that is a very, 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 very complex topic. So, but now what's interesting from a scientific computing perspective, because we're all HPC people, we may not care about the application of how to do it. We may care about the computations that are involved. Many of us have been working on scientific computing. We all know these sparse matrices from scientific computing. We all know sparse computations. These sparse matrices, they have a lot of structure in here. You see this as usually localized communication. You see it's not a random matrix. This is a huge difference to actual language models. So now we look at BERT. This is the mascot for the first language model. Actually, there's a whole Sesame Street version. There's Big Bird, like every single Sesame Street character. In fact, in China, the most popular language model is Ernie. So that's what I'm hearing. Okay, so but now we take 2 layers out of BERT. Actually, we're taking the WQ and WK matrices, in case you're familiar with that, from the 3rd encoder in BERT. That's just randomly chosen. And we sparsify these matrices. And you see the sparsity counting up here. From 0, everything is black. Black means not sparse, white means sparse. And it's counting up to 1 for these two matrices. You can see there's basically no structure. There is actually some structure. There's these lines. You see faint lines here. Actually, we use these faint lines in our latest research, but for the unpracticed eye, there's very little structure. What does this mean? That deep learning matrices are very, very, very different from scientific computing matrices. This gives rise to a new architecture that is tuned for deep learning, how to do these things. What is this architecture? N-to-M sparsity. This is what NVIDIA put in their tensor cores. They put a very limited version of N-to-M sparsity into it. It's a 2 to 4 sparsity. Basically, out of a block, out of 4 elements, only 2 are non-zero, or exactly 2 are non-zero. You can extend this to 16 to 9, or 16 to 8, or something like this. So there's a whole lot of research going on how to build these architectures. In my group, what we've been building, actually, again, this paper, we've been building a particular framework on top of PyTorch to do sparse model inference and sparse model training. I don't have enough time to go into details. But at the end, what happened with this framework is that we used the 2 to 6 sparse format on CPUs. So you can also implement this on CPUs. It's not very fast, but it's faster than nothing. And we sparsified all of the layers in the standard BERT model. And we achieved about a 32% speed up. That's pretty sad. You're like, okay, that's 32%. But later what we did is we did a similar thing on GPUs. We used the 2 to 4 sparsity that is in hardware on the GPU, and we pumped it up to higher sparsity ratios, to arbitrary N-to-M sparsity. It's not fully arbitrary, but it's more than 2 to 4, and we achieved a 10x speed up, and that was the paper at Supercomputing last year. So here we got another 10x on GPUs for language models. So actually today we have even slightly better results. The next step, and this is going to be published at iClear in Vienna in 2 weeks, is actually merge quantization and sparsification together, right? Obvious. That's what we call the sparse quantized representation for weight compression, and that's SPQR. Like, we came here to win, and we're close to these people, actually. So now we got a factor of 100 times. Like I give you 2 factors of 10, like 1 for the quantization, 1 for the compression. So now the question is, how do we get the last factor of 10? And that's for the training in the network. After all, we all care about the network. Here, what we have to figure out is how do we actually do communication in these models? So just to give you a little bit of an overview, many of you have seen this before. This is a slide deck I'm using typically, so I'm going a little bit faster. I hope that you remember, but I still want to refresh our memories here. So we have, in deep learning, we have multiple so-called mini-batches, pages of text. Right? So this is what we feed into the model. So we have 4 or 5 mini-batches in this case. And these mini-batches are essentially units of statistical update. So this is, once I run these 3 pages through the model, I'm updating my parameters and then running the next 3 pages through the model. So what I do is actually, I take this first mini-batch and I cut it into 3 pieces, page 1, page 2, and page 3. Then I run these 3 pieces through 3 separate copies of the language model, like complete copies. Now the problem is, each of these copies is still 700 gigabyte in size. So I don't have a 700 gigabyte GPU to run this on. So what I need to do now is I need to cut each of these copies, that is each 700 gigabyte, into smaller pieces. Oh, the projector is not great, but I can cut it into these different layers. So first layer, second layer, third layer, such that it fits my GPUs. Right? So if I have 100 gigabyte, I cut it into 7 pieces, for example, 100 gigabyte memory on the GPU. Now, this doesn't actually make it faster, it just makes it slower, because now I have to distribute my weights to multiple GPUs just to make them fit. If I now want to make it faster, because you may have realized that the Copilot is quite slow, to make it faster, what you would do is you would now parallelize each of these layers, which I call operator parallelism. Many people call this tensor parallelism, but again, it's not really a tensor, so we can talk about that later. But we can parallelize each of these layers to now make it faster. And I want to give you a whirlwind tour now in about 5 minutes to how to do these parallelizations, how to pull some tricks for each of these parallelizations. So it's going to be fast, but bear with me. For the gradients on the backward pass, which is actually the core of data parallelism, what you can do, and it's very, very, very interesting, you can actually skip or drop 90 to 99.9% of these values. It's another form of sparsity. You can just remove them, not send them over the network. You accumulate them locally. Not fully remove them, but you just don't send them. And it'll be perfectly fine. Like here's a training run for a ResNet, and here we have the baseline is in blue. This is my training loss, so it should go down. This is good. If I'm discarding 99.8% of the values, I essentially get to the same result. Right? So you don't really need a network, great. So we can pack up and move, and that's it. Well, that's for data parallelism. We need the network for the other forms of parallelism. For pipeline parallelism is now interesting. Pipeline parallelism is a little bit more complicated, because what I'm doing here is I take the model, which is now drawn from top to bottom, so 3 layers, 1 layer, 2 layer, 3 layers, and I have different stages. I cut this into 4 stages, so let's say it's 4 layers in this case. So what I now do is I have 4 accelerators: accelerator 1, accelerator 2, accelerator 3, accelerator 4, and now the first mini batch moves from accelerator 1 to 2 to 3 to 4. So this is time, this direction, and then it moves back up because that's the backward pass. So this is my f of x that I had on this slide, forward pass, and now I need to do the gradients on the backward pass, and then I do this. The way to do this is, of course, you start your second mini batch immediately when you can, but then you see, oh, I have this backward thing here. So I'm using the last accelerator twice. So that creates a bubble here, that creates holes, because I have to go back. This is quite annoying. But what we found is that actually if you just draw this model in a different form, like from bottom, so this is from top to bottom, this is from bottom to top, do the same thing, you see now I'm coming from the bottom to the top. And actually, if you now look at this downward and upward pass, and if you merge these 2 pipelines, you see, it fits perfectly together and you have very little bubbles. Right? So that's a double pipelining scheme where you just have an upward and a downward pipeline running at the same time on the same accelerators. It's quite cool, and this is what many people are doing today. This is also possible if you're a machine learning expert. You will say, oh, but the backward pass is twice as long as the forward pass, and you're cheating, your image is not right. Yeah, I'm drawing it here for the twice as long backward pass. It also works. Right, so just if you're an expert, but at the high level, that's the same thing. You can run this in practice. You will see it gets you a lot of speed up, so it's about 2 times faster because you reduce these bubbles. It's not 10, it's 2, because there were not so many bubbles if you counted it. But you can get a 2 times speed up, and that's of course important if you have a thing that costs you $13 million to train. Cool, and then the last one, the operator parallelism, one trick to show there is very, very simple, and I don't want to spend much time. It's literally just realize that the operators are just matrix multiplications. There's 99.8% matrix multiplication. So what you need there is literally, you just need parallel matrix multiplication. And here we have a framework that's called Cosma, that's parallel matrix multiplication that was developed with the team of Joost at CSCS. That immediately fits operator parallelism for deep learning. It doesn't really immediately fit because it has FP64 and we really need FP32, but people have adopted similar techniques to make it work in practice to do operator parallelism with the same scientific background, not the same software, but the same scientific ideas. In fact, AutoDDL does that really nice at the end. Okay, cool. So now we have understood how we parallelize deep learning workloads. That was my promised 5 minutes. I'm perfectly in time. I'm sorry if that was a little bit fast, because usually that's a full lecture of 1 hour. But I'm trying to give you an overview, as I mentioned. And you can always dive deeper and go to YouTube and watch more videos or read it in the internet. There's a lot of information here. But now if you look at the communication pattern, because after all, we're here for networking literally human networking, but also computer networking, which is what I just meant. We have data parallelism, pipeline parallelism, and operator parallelism. These are the 3 fundamental pieces of parallelism we have. Okay? So now, one insight is that for the data parallelism, we run all reduce. Okay? For the pipeline parallelism, and this is, like if I'm drawing it like this is model replica 1, replica 2, replica D, we run this in this dimension. In pipeline parallelism, we have the pipeline stages 1, 2, 3, and then we run it in this dimension. The operator parallelism, we cut each of these operators in the vertical dimension here. We run all reduce, which is how you do matrix multiplication, parallel matrix in this dimension. So we see we are basically running in a 3-dimensional shape. And at the end, if we put these all together, we are running a 3-dimensional torus workload overall. And so this is quite nice, because actually what you realize when you build AI systems, you realize that you can never have enough network bandwidth. Like this is, you see this very clearly, because if you go back to 2021, a TPU v2 had 1 terabit per second. Like 3 years ago, they already had 1 terabit per second network bandwidth. Well, if you look at the ALP system that Thomas talked about, it has 200 gigabit per second network bandwidth. That's a fifth of the bandwidth of a system that people built 3 years ago, right? So that's quite low. And this is a perfectly well-designed system, because for HPC, you don't need that high network bandwidth. For AI, you need a lot of network bandwidth. And it's just witnessed by other systems, like the AWS training system, 1.6 terabit per second in 2021. The A100, actually, if you count the NVLink connectivity of an A100, we go to 4.8 terabit per second. Unfortunately, it doesn't reach a whole lot, so it's only in a node, essentially, this NVLink bandwidth. And then Tesla's Dojo, like Elon Musk was announcing that in 2022, they wanted to build a system with 128 terabits per second, just as a comparison point. The NVIDIA Spectrum 4 switch or the Tomahawk 5 switch, a network switch, a thing that is built to move data, has only 52 terabits per second. An AI accelerator has more network bandwidth than a freaking network switch. Right? So think about that. That is also an interesting one. Since then, by the way, Tesla, Dojo has been paddling back a little bit because they realized actually very hard to build that much network bandwidth. That was their plan. I think at now the last one announced was about 60 or so, still higher than a network switch. But this is the challenge. If you would now just cable up a fat tree with 16,000 endpoints, with 16,000 accelerators, this network alone would cost you $680 million, and you have not bought a single accelerator, right? That's just the network cost. So that's ridiculous. I mean, nobody can afford this, obviously. So what you need to do is you need to be a little bit more saving. And here I want to quickly show an architecture that I and colleagues developed at Microsoft. I don't have enough time to go into details, but at the end, it's a two-dimensional structure. This is very much like the latest TPU, but we did it earlier. So where you have a 4x4 board or whatever, a 2x2 board, K by K board, and then connect this fully in each dimension, such that you only have a single network switch in each dimension. So you save a lot on network switches, essentially. You save a lot of cabling. And after all, this topology is somehow a trade-off between a global fat tree, which is super expensive, a local topology like a 2D torus, which was TPU v2, which is very, very limited, and it lies in between because it has some switches and some local connectivity, and we call it Hemming mesh in case you want to look it up, the exact topology. So there's a nice trade-off, blah, blah, blah. So now I have about, I want to conclude that part, and we've now seen 1,000x improvement because that topology is about 15 times cheaper than a global fat tree. So now I want to use the last 8 minutes, if I may. I mean, I can be a little bit faster in case there are questions. How do we do this, Hussein? I'll take the 8-minute version, maybe 6 or so. I want to give you some predictions that the AI field, how the AI field is driving high-performance computing. Because I've only talked about AI so far. I'm an HPC guy, right? So you may not have realized this, but I grew up with HPC. My background is MPI, my background is scientific computing. So there is a tremendous impact that what I just talked about, the trillion-dollar business coming up in about 5-6 years, it's going to be a trillion-dollar business. That's what Bloomberg predicted. That business is going to impact HPC in massive ways, and we need to understand how to react to this. My first prediction is accelerators converge, basically because AI is a gravity well and HPC will follow. And we've seen this in Jensen's announcement of the Blackwell architecture. And there are not too many details known, but what is known is it's not going to be strong in FP64. Right? It's going to be very strong in AI data types. And we can see this also announced by AMD. So AMD at ISCCC 23, Lisa Su, the CEO, she was presenting this plot here where she showed that there is a 30x benefit going from FP64 to FP8. Well, just a couple of weeks later, Jensen was talking about the same thing. Of course, while AMD had it on plots, Jensen had an architecture ready to sell. Come here, get some. Where actually on the NVIDIA H100 SXM, the FP64 Tensor Core is 67 teraflops. The FP8 Tensor Core is not 8 times faster, it's 30 times faster. This is just because there's a quadratic scaling in these units, and I can also go more into detail, but I don't have enough time. So keep that in mind. As you're reducing the bit width of your calculation, you're gaining more than just the linear factor that you would expect. You're gaining much more, so 30 times. For Blackwell, it's even more aggressive, I think, but I don't know details. So what this basically means that these modern architectures, these future architectures, they will support vector scaling, a thing I didn't have the chance to talk about, but this is what we actually do in machine learning, and 0 points automatically in hardware. Like this is what some vendors will actually build this, and they will be super optimized for this data movement because they realize the computation is nearly free. Right? This is actually true. Right? This is nearly free. You really must have a very complex data movement system to make this happen, and this will have two impacts for us. Latency will be a problem, and locality and sparse connectivity will be a problem. So if you're doing research in this field, focus on latency and focus on sparse connectivity and locality in general, because data movement, right? That's how to work with it. Actually, Bob Wisniewski from Samsung has given a very nice talk in our seminar how to address these things in a future computer architecture. And also the topology I just talked about, Hamming mesh, but there's also a full YouTube video in case you care, is fully explaining how to do this. So now prediction number 2 is programming tools converge. So we all love Fortran, isn't it? So you love, I'm sure the audience loves Fortran. Many climate scientists really like this, but unfortunately, it may not survive the AI hype, because what's going to happen is that data science is mainly driving Python today, the Python ecosystem. There are some smaller ones trying to pop up, but they're not really winning against the Python ecosystem. So HPC will follow this whole thing. If you just look at the most popular programming languages, Python passed C very recently. So it's not all Python. I'm not a big fan of Python, by the way. The syntax is, but this is what's happening. The ecosystem takes over, and it's really the ecosystem. It's not the language design that's beautiful. It's not easy to program or whatnot, maybe, but not for me. But certainly the ecosystem. All of the AI tools are written in Python, like TensorFlow, PyTorch, all of the plotting tools, everything is written in Python. So we just have to deal with it. What we actually do in my group is we try to make Python amenable to high-performance computing, because Python is really slow. It's like a factor of 10 to 1,000 slower than a well-written Fortran code. So what we do is we basically build abstraction layers for domain scientists to work in Python, and then have an internal representation in our DACE framework to actually have a computer scientist or performance engineer rewrite these Python codes with what I would call performance meta programs into different representations such that they execute fast on modern hardware. And at the end, we are going from tens of lines of code. By the way, all of ChatGPT, the whole training model, the whole training background is less than 100 lines of code Python. Right? There's a whole lot of infrastructure underneath, but the scientist never sees that. The scientist just calls linear layer forward, multi-head attention, and puts those together. Then all the action is happening here, and at the end we are generating a lot of code that's very close to assembly code. So the last prediction, thank you, last prediction is that these networks are converging. So what does that mean? Because actually slightly differently from the previous one, I would be claiming that in this case cloud computing is the gravity well, because what we are seeing right now is we are seeing that mega data center providers field the largest supercomputers on the planet. This is unbelievable. To me, this is unbelievable, because we used to have these computing centers like CSCS, big DOE centers like Argonne, Livermore, built the largest machines on the planet when I was young. Right? Now, forget it. Forget it. They sit in private data centers locked up in Boynton, Virginia or somewhere, next to a power plant, typically, and run the largest workloads on the planet. So the industry is realizing this. So industry is moving on this AI field, and this is why I've actually been working with some colleagues to write up a little overview of how this converges. Because at the end, these data center providers, they need HPC technologies. They don't realize this yet, but they need it. For deep learning, we need HPC networking technologies. NVIDIA has it right now. NVIDIA has the full market share, essentially. That's not making cloud providers happy, because now you can dictate prices, right? So now you can actually see in cloud HPC today, it's quite competitive to on-prem HPC. So they have, in the cloud, they have various techniques that are already pretty good. I can't go into detail. What we then realized, and I'm helping Microsoft to succeed in this field as a typical hyperscaler, is that, hey, what we do today with Rocky is not a great fit for these very large-scale workloads. So that's another paper that we wrote together with Microsoft here, many people, also Google and various people from Broadcom and HPE, trying to define how we would build an Ethernet-based network that is good at HPC and AI for the cloud. And the result of this was essentially, or what was this inspiring, was the Ultra Ethernet Consortium, where people get together to build an industry standard, because InfiniBand now is 30 years old, to build a new industry standard that modernizes the new insights. For example, InfiniBand was designed for NICs with very little compute capability 30 years ago. Today, NICs have a lot of compute capability, actually more than you can imagine. Right? Connect X7 is just crazy, for example. We have a bunch of founding members. One is prominently missing. And we have various white papers going. Oh, that may be changing. We have various white papers going ahead. So with that, I want to summarize. what I talked about. So I talked about how to build very large systems for this learning. I talked about programming sparse models. I talked about the co-design. Then these 3 predictions, one for accelerators, one for programming tools, and the last one for networks. And then if you care about this, I would recommend to read the networking papers on the bottom, because they're kind of outlining what the mega data center providers need. So this is what I was able to pull outside from one of these mega data center providers. So thank you very much, and I'm not sure if there's time for questions, but I'll be here at least during the break. Thank you.